All right, let's jump right into this explainer. Today, we're demystifying the absolute powerhouse driving our entire digital world. I mean, whether you're watching this on a tiny phone, a tablet, or some massive custom-built desktop rig, there's a hidden, furious little engine running the whole show behind the glass. Yep, we're talking about the Central Processing Unit, or CPU.
Here's our roadmap for today. First, we'll meet your computer's brain. Second, we're stepping inside the silicone kitchen. Third, we'll break down the fetch, decode, execute cycle. Fourth, we'll trace the journey from room-sized machines to microchips. And finally, we'll look at the modern CPU era.
All right, starting off with part one, meet your computer's brain. What exactly is a CPU anyway?
So at its absolute core, a CPU is basically just an incredibly fast, fiercely obedient instruction follower. It doesn't actually think on its own. Instead, it just relentlessly hammers through three simple steps. It fetches an instruction, it decodes what that instruction actually means, and then it executes it over and over and over again. It's really the grand architect of all the logic inside your device.
Moving on to part two. Let's step inside the silicone kitchen and look at the main components of a CPU.
Okay, to really wrap our heads around this hardware, let's imagine the CPU as a master chef running a high-end kitchen. First up, the control unit, or CU. This is the chef's brain. It's the ultimate manager, dictating the flow of data, telling everyone what to do, and, crucially, when to do it. Then you've got the registers. Think of these as the pre-measured ingredients sitting right there on the chef's prep table. It's ultra-fast memory built directly into the CPU, holding the exact data and instructions needed for this very second. And finally, the ALU, the arithmetic logic unit. This is the actual cooking process. If your computer needs to add 5 and 3, or run and, or, and not logic operations, the ALU is where the heat gets turned up and the actual math happens.
But even a master chef needs a bit of backup to keep a 5-star place running smoothly. First, they need recipes, right? That's your ISA or instruction set architecture. It defines the specific language or recipes the CPU actually understands, like x86 or ARM. Then there's cache memory. Think of this as a super quick access pantry. It's a tiny, lightning-fast memory sitting right between the CPU and your main RAM. It holds frequently used stuff, so our chef doesn't have to walk all the way down the hall to the walk-in fridge every single time they need a pinch of salt. And lastly, you need a waiter to shuttle things back and forth. That is, your bus system, seamlessly moving data between the CPU, the memory, and your input/output devices. All right, on to part 3, the fetch, decode, execute cycle. Let's see how the CPU actually works, step by step.
This 4-step flow right here is literally the heartbeat of your entire computer. Step 1, fetch. The CPU grabs the next instruction from memory using an address stored in a special register called the program counter. Step 2, decode. The control unit looks at that instruction and translates it. It figures out, oh, okay, this is an add command. Step 3, execute. The ALU steps up and does the actual math. And step 4, store. That brand new result gets saved right back to a register or out to main memory. Fetch, decode, execute, store. Boom, boom, boom.
Now, modern CPUs are insanely fast, and that's largely because they don't just cook one meal at a time anymore. They use a brilliant trick called pipelining. Basically, they run multiple instructions in parallel. So while instruction number 1 is at the execute stage, instruction number 2 is already being decoded, and instruction number 3 is just being fetched. By stacking and overlapping these stages, fetch, decode, execute, memory access, and write back, the CPU is maximizing its efficiency. Literally no part of that kitchen is ever just standing around waiting. To really grasp the scale of what we're talking about, we have to look at the clock signal. See, CPUs operate on a rhythmic electrical pulse. A pretty standard 3 GHz processor, it repeats that entire fetch, decode, execute cycle a mind-numbing 3 billion times every single second. So when you just casually click your mouse or tap a screen, literally billions of tiny mathematical cooking steps fire off instantly to make it happen. It's just wild.
So knowing all those insane mechanics, it really begs the obvious question. How in the world did humans manage to shrink this wildly complex setup down so small that it fits on the tip of your finger?
That brings us to part 4. From rooms to microchips, the historical evolution of the CPU.
Believe it or not, this whole journey started way before electricity was even a thing. Back in the 1800s, visionaries like Charles Babbage were designing the analytical engine, which was basically the very first concept of a programmable mechanical machine. And Ada Lovelace, she actually wrote the very first algorithm for it. Now, sure, there wasn't a real physical CPU yet, but that foundational spark, the core idea of a programmable processor, it was absolutely born right then and there.
The contrast here is just staggering when you look at the leap from the 40s to the 70s. Think about the 1940s ENIAC. These early machines used vacuum tubes. They were massive, absolutely power-hungry, famously unreliable, and took up entire rooms. And the CPU wasn't even one cohesive thing. It existed as a bunch of sprawling, separate circuits. But then, fast forward to the 1970s, the birth of the microprocessor. In 1971, the Intel 404 completely flipped the script. It was just a 4-bit processor, sure, but the absolute game changer was that the entire CPU was finally integrated onto a single, solitary integrated circuit. The whole shebang on one chip.
This timeline perfectly maps out that relentless, accelerating drive to shrink everything down. We kicked off with those massive, room-sized vacuum tubes in the 40s. By the 60s, transistors came along and swapped them out, making things smaller, faster, and way more reliable. That transistor boom is exactly what birthed those single-chip microprocessors in the 70s. And from there, the miniaturization just kept speeding up, faster and faster, launching us straight into the incredibly dense multi-core era of the 2000s.
And that leads us into our final section, Part 5, the modern CPU era, from personal computers to AI chips. So, the 80s and 90s really kicked off the true personal computer era. This is when CPUs finally hit that sweet spot. They got powerful enough and affordable enough to actually put in our homes. We're talking legendary processors here, like the iconic Intel 8086, which literally laid the groundwork for the x86 architecture we are still using today. And of course, the incredibly famous Intel Pentium line. This era took those advanced concepts we mentioned earlier, pipelining, cache memory, floating point units, and pulled them right out of the research labs and put them onto our home desks.
Then, by the 2000s, the game totally shifted again. Instead of just trying to make one single core run faster and run hotter, giants like Intel and AMD started cramming multiple cores into single chips. That gave us desktop absolute beasts like the Core i7 and the Ryzen series. At the exact same time, a massive mobile revolution was kicking off. Super efficient ARM-based chips became the brains of pretty much every smartphone on the planet. And more recently, we've seen Apple shake things up by designing their own custom M-series chips, combining just ridiculous computing power with very, very low energy use.
Which brings us to today. In the 2020s, the architecture is evolving all over again. We're now seeing processors specifically custom-built for heavy AI tasks. We've got ultra-low power designs created specifically to run the IoT, the Internet of Things. And we're seeing this massive shift towards chiplets and heterogeneous computing. Think of designs like the Apple M1, where you have different types of highly specialized processors all bundled really tightly together to get maximum efficiency out of every single watt.
If you take away absolutely nothing else from this explainer, let it be this staggering reality of miniaturization. I mean, we started in an era where the word CPU meant a bunch of massive, separate components spread out across an entire room. And now, a CPU equals literally billions of microscopic transistors perfectly organized onto a tiny piece of silicon no bigger than a postage stamp.
It really leaves us with a fascinating thought about the future of all this hardware. We've been riding this incredible wave of shrinking transistors for decades now, cramming more and more cooking power into our silicon kitchens. But as we push deeper into the era of AI and these microscopic atomic-scale chiplets, you really have to wonder, just how much further can we possibly shrink the kitchen before we hit the absolute hard limits of nature? Are we going to have to invent entirely new physics just to cook our digital recipes? It's an absolutely incredible time to be following this tech. Thanks for jumping into this explainer with me today.